finance like there's no tomorrow.
Hello everyone, welcome to the course of Financial Engineering. My name is Grzelak and I'm the course instructor. This course is focused on interest rates and XVA. However, we'll be also discussing in different asset classes like inflation and foreign exchange. The main objective of this course is to be able to price multiple linear products in those asset classes and at the end, ultimately, to be able to calculate XVA, I mean here CVA, BCVA, BCVA and FVA, and also evaluate value of risk of your portfolio. So first, we will gain knowledge how to build a portfolio consisting of multiple asset classes, and then ultimately at the end of this course we'll be applying risk measures like XVA and also value at risk, historical value at risk, and also Monte Carlo based value at risk. We will be applying those risk measures to portfolio that will be able to derive and develop over course of this 14 lectures. Let's take a look at the main objectives of this course. So the main focus is the modeling of interest rates, while other asset classes like foreign exchange and inflation will be also covered. So you see here we are talking also about the type of hybrid models that we are looking also at the correlations between different asset classes like here foreign exchange, inflation, stocks, and so on. Ultimately, after completing the course, the student or yourself, you should be able to build a multi-asset portfolio consisting of linear products and perform XVA and then of course value at risk computations. So here of course the simulation of asset classes or multi-asset classes, it requires some knowledge that you have to have beforehand. In this course, I will explain the basics, how to build up a model consisting of stochastic differential equations for multiple asset classes, how to correlate those different processes, and how to use them in pricing of derivatives. What is the expected prior knowledge? So, of course, we need to know something about stochastic differential equations. So we are expressing risks or risk factors in this lecture in terms of SDEs. We need to also know something about numerical simulation, numerical methods. Mainly will be focused in this course on Monte Carlo. And this is also market practice or industrial practice, especially in the context of FVA or XVA in general, and also value at risk. And then prior to this course, I would highly recommend if you follow the course of Computational Finance. The description of the links to this course you will find on this channel in the links in the description of this video. So the workload. I have prepared 14 lectures and each lecture, so some of those lectures, as you will see in a few slides, they are bigger than others because sometimes the subjects require much more attention. So it's difficult to squeeze all the materials to about 1.5 hours. This is typically the length of the lecture. So I have divided 14 lectures into blocks. So depending on the materials and the workload, and those blocks typically are between 45 minutes and an hour. And so this is about 45 minutes, 60 minutes, sometimes it is maybe 70 minutes, but not too often. And then we have about 32 blocks. So as you can see, we have 32 times we will meet each other in this series of lectures. Every lecture, so not every block, but every lecture where we finish big piece of materials, then we have a homework assignment. So homework assignments are given at the end of each lecture. I have prepared from sometimes 1, sometimes 2, sometimes even 4 homework assignments. For many of those homework assignments, you will find a solution online, and you will find a solution on this, maybe in the description of this video. You will also find the links to the solutions. However, not for every assignment. For some of the assignments, they are very much subjective. So this means you have to be a little bit of creative, and there is no maybe ultimate answer how to solve it, because, for example, you may need to download some data regarding stocks, and you have to perform your simulation yourself. So, of course, in that case, it is not possible to find one solution that you will be answering the questions you have been asked. The programming language, it's Python. In this course, as you will see now, for example, I'll be working the same as I was performing this task in the course of computational finance. We'll be often switching to Spider. So this is the interface for coding, and we will be going through the code together. For every lecture, basically, there's from about 3 to 5, maybe sometimes Python goals that we'll be discussing. So at the end, it is not only about the theoretical knowledge about the content of this series, but we'll be also discussing some details with regards to implementation, efficiency, and at the end, we want to build a portfolio. So it's not only theoretical way how we would build it based on SDEs. We need to put all those pieces together, and at the end, we need to have a code that will perform the task of calculations of value at risk and also XVA. So at the end, we need to have all those tools available. Codes for Python codes for this lecture are also available, freely available. So you can find it also in the link in the description of this video. I have put basically all the lectures in Python codes on GitHub, so you can easily download those and use it once you'll be following these lectures. So, of course, the materials of the course, so we are here right now. All the materials of this course is self-contained. This means that everything that you need to follow the code and also to learn the material necessary to be able to complete your homework assignment and also the project at the end of calculating XVA, everything you will find in this course. However, this course is based on a book of mathematical modeling and computation in finance, and also you will find description in the description of this video. However, this course is not really about the book. It's based on the book. If you would like to do some extra assignments, I highly recommend to use the book. However, it is not really necessary. Let's take a look at the course roadmap. So what are exactly the subjects that we would like to discuss in this course? So you see we have 14 lectures, so it's a rather long way up. So this is Mount Everest, and we are today in the base camp. We are starting this lecture with introduction and overview of the course. So we'll be discussing each of these lectures today, what are the subjects and how those topics will contribute to our ultimate goal of the XVA and VAR calculation. So this is basically 2 topics at the end. Of course, the summary, of course, of this course is on the top, but already if we are able to perform these 2, so basically, let's say these 3 subjects should be on the top of this mountain. So we start with lecture number 1, so it's today, overview of the course. Lecture number 2, it is very important block necessary to understand and also be able to think in terms of XVA simulation or the exposure simulation. Then we'll be talking about filtrations and measures. So without understanding concept of filtration and measures, you will not be able to perform your exposure calculation in an efficient way. You really need to understand what are the important elements of these techniques and actually of this theory to really understand what models you are able to use for your exposure simulation for your ultimate goal of XVA. Then after we understand the filtrations and measures, we go to the interest rate world of HJM framework. We will be discussing different features of the framework, why this framework is so important, what models fit to that framework, and how this will fit, let's say, to the whole goal to get to the top of this mountain. Lecture number 4, it's about short rate models and dynamics of yield curve. We will have quite some lectures, so it's I think 2 or 3 lectures very much concentrated on building of a yield curve and also relation of a yield curve under different stochastic models. And this is the first one. We'll be looking at the short rates. In particular, we'll be looking at the Hull-White model, also Hull-White 2-factor model, and we'll be observing the dynamics of a yield curve. And based on that, we'll be comparing multi-factor to single-factor models, and we'll be judging which model is more suitable for realistic scenarios of a yield curve. So this is kind of very important element. I have performed also quite very interesting analysis in this lecture. We'll be doing very much hands-on exercise. We'll be looking at the real market data, observing how historically S&P behaved, and at every historical date, there was a yield curve basically, and that dynamics of a yield curve. In this lecture, we'll be trying to mimic using full white and full white two-factor models. So you will see it will be a very insightful lecture. In lecture number 5, we will learn how to apply our knowledge about measures, filtrations, and stochastic models, and we will be pricing interest rate products. He'll be talking about mainly about linear and also products that depend on volatilities. Of course, the main volatility product that we want to discuss is swaptions. This will be discussed in lecture number 7. After we know about interest rate products, we know about short rates, we know about a little bit about the yield curve. We move to lecture number 6, where we will discuss the topic of yield curve construction. How to construct a yield curve, how to build multi-curves, what are spine points, those details about the yield curves, how to choose interpolation once you construct a yield curve, and also here we'll be building everything from scratch using Python code. So at the end of this lecture, you'll be able to build your own yield curve, given market instruments, given interest rate products. Lecture number 7, so we go a little bit more higher. So now we are talking about the swaptions and negative interest rates. So how to handle negative interest rates in the, let's say, interest rate world, and also the topic of swaptions. This is also very important, as you will see later in this course. Then we go a little bit sideways, this topic about mortgages and prepayments. Although this subject maybe is not perfectly fitted to the, let's say, to the problem of valuation calculations, of the valuation adjustments of exposures. However, it is a very fascinating subject where we can merge, where we combine the concept of pricing under the risk neutral measure and also pricing under the P measure. And this is really, really interesting. And of course, to price mortgages and prepayment risks. So those risks are associated with clients that prepaid their mortgage sooner than contractual agreement. For this, we also need to know about the filtrations, measures, and pricing. So this is also a very interesting subject, and we will spend quite some time, quite a few hours actually on this subject itself. After we know how to build curves and about interest rate products, we need to move to the case of hybrid models. Of course, ultimately, we don't want to have only portfolio of interest rates. We also would like to include foreign exchange, inflation, and stocks. In lecture number 9, we will concentrate on how to develop Monte Carlo engine for those multi-asset models. Lecture number 10, we'll concentrate on foreign exchange and inflation. So I'll show you first, of course, how to use this knowledge from hybrid models to price derivatives. In foreign exchange and inflation, we'll be talking about both linear products like forwards and also about options. So this is also nicely will cover fit to the concept of interest rates. Lecture number 11 is about market models and convexity adjustments. Once we talk about the HJM framework, we should not only think about short rate models, we should also think about more advanced models. I always call it a problem solver models. So for example, LIBOR market model definitely belongs to this category. It's very advanced and sophisticated methodology. However, it allows you to price all sorts of interest rate products that short rate would not be able. So you will understand why people often use LIBOR market model, what are the problems with the LIBOR market model, and how to make it, how to improve it with, for example, stochastic volatility, and also how to destroy it by some approximation techniques that often abuse in practice. And then, of course, convexity adjustment. I'll explain the concept of convexity adjustment and convexity in general in terms of measures and pricing. So this will be nice, also nice lecture here. Now we are almost on the top of this course. We're almost finished. We have lecture number 12. We'll be talking about exposure calculations. So using our portfolio that we have built over the course of this lecture, here we'll be evaluating exposures. We are looking at the risks associated with a value of our portfolio in time. And then we'll be looking at some value adjustment measures like a CVA, BCVA, and FVA. And later, For the same portfolio or similar portfolio, we will be calculating historical value at risk, stressed value at risk, and also expected shortfall. So this is also perspective, maybe not from a pricing perspective when we think about risk-neutral pricing, but here, lecture 13 will be maybe more from perspective of a risk manager, how to manage your risks, how to measure those risks, and what are the insights of the method. And of course, here also everything will be based on coding, so we'll be downloading data from the market, and we'll be using this data to calculate historical VAR, SVAR, and expected shortfall. So everything will be really hands-on, and at the end of this course, of this lecture, we'll be analyzing the results. Lecture number 14, this is really the end. There we will summarize what we have learned in this course. As I mentioned, every lecture will have a few assignments that you have to perform, and everywhere we will also do some Python coding. So it will be really hands-on, and I hope that will be a very enjoyable series of lectures. As the start of this journey to simulate our exposures and XVA, we have to start with a basic concept that is necessary to continue to be able to do the simulations that we will do in the later part of this course, is the concept of filtration and measure changes. So this will be covered in lecture number 2. It will be about understanding of filtrations and measure changes. As you can see here, I prepared a photo back to the future, because if you are messing up something, if you make a mistake in your concept of filtrations, if you're not handling it properly, that may lead you to the very severe consequences as presented in that movie. So in this lecture, we will concentrate on how to look at filtrations and measures, what are important elements, and how to make a mistake in the calculations of exposures. Of course, I will also show you very significant benefits of using measure changes, conditional expectations, of course, filtrations. So this lecture is about 2.5 hours. So we will have 3 blocks. So I have divided this lecture into 3 elements. In the first block, we will talk about filtrations, conditional expectations, and also simulation in Python. I will show you how to use the conditional expectation in Python, what are the problems we can solve in simulation. Typically, when people talk about the conditional expectations, it is always associated or often associated with some kind of theoretical aspects. He'll be also having hands-on exercise, how to simulate this expectation and how this is related to the so-called nested Monte Carlo. So it'll be also some kind of interesting concept to understand. In the second block, I will show you how to use the concept of conditional expectation to option pricing. How you can benefit from this concept into improving your simulation and pricing of a derivative. That'll be also it's a very much engineering trick, or let's say it's a very elegant way of expressing option prices in terms of conditional expectations. In essence, you can think that if you have a very complicated model, that you know that if the parameter of this model is constant, for example, and then this model would collapse to some kind of much simplified closed form solution that you have already solution to, then you can use the concept of conditional expectations, and then you can benefit in your overall convergence. And that will be also shown in the next experiment. And then we move to the measure change concept. So change of numerière or concept of numerière, what is it and how to use it. We start with a changing measure from a real world measure P to Q under the Black-Scholes model. And then I will show you what are the most typical measures that we have to deal in the financial engineering world. And I will show you also how we, by changing measure, we can actually, from rather complicated problem, the problem may collapse to something very trivial, very elegant, and very nice. So how to use measure changes to benefit, how to simplify your problem by that technique. And here I will talk about 3 different measures. We will be talking about a stock measure. So how to use stock measure to solve some kind of pricing problem, dimension reduction, how change of measure may reduce your complexity of the problem, and then we have also T-forward measure. This is also very important, especially in the world of interest rates. And finally, we'll move to the summary of the lecture, and also there will be a homework assignment. After lecture 2, we go to lecture number 3, where we'll be discussing the framework of HJM. This lecture, it is divided in 2 blocks. As you can see, I have prepared some kind of vehicles or cars, you can think, and those 3 vehicles will be linked to the models discussed in this class. In particular, we'll be talking about the equilibrium model, short rate models, and also LIBOR market model. Maybe now I don't want to explain which of those categories or which one of those vehicles would fit to each category. This will be explained in that lecture. But as you can see, we may have 3 different, let's say, categories of models. Some of them are, let's say, old-fashioned. Some of them are very fast, elegant, however, not maybe very practical. And some of those models can be considered a problem solver, however, maybe in the cost of maintenance that is very, very high. So you see, this will be basically the message of this lecture. We'll be talking about the framework for the HJM. I will show you how to derive the dynamics for the processes in this class. And in particular, we'll be talking about full-E and short in a full-white model, and also other possible extensions. So we will start with equilibrium versus term structure models. And also here we'll be talking about the HJM framework. What is the history, where it comes from, what are the assumptions of the framework, and why actually this framework is so much important in the interest rate world. And then we link this HJM framework to the framework of the instantaneous forward rate. So this is basically part number 2, part number 1. In part number 2, we'll be talking about arbitrage-free conditions that are imposed in this framework. Then we go through some simulations, Monte Carlo simulations of Python, and in Python of a full-E and a full-white model, and then will be also homework assignment. So here I will show you how those short rate models discussed here, the full-E and full-white, will fit to the HJM framework, how they are linked. Actually, in this case, how by specifying volatility under the HJM framework, you may arrive at short rate models. That they're consistent and also very elegant in the sense that if the model belongs to the class of HJM, essentially, if you simulate such a model, it replicates the yield curve exactly. So you specify a yield curve, which is an input to the model, and then model always calibrates perfectly to yield curve. And that will be different for equilibrium models, for which yield curve is an output. It always needs to be recalibrated. But details on this, and we'll spend some time on that, will be in lecture number 3. Lecture number 4 is focused on yield curve dynamics under short rate. So this will be introductory part. What is yield curve? How it's defined? What kind of shapes of yield curve we may have? And then how this is related on how that can be modeled by short rate. Here at this point, we are not building yield curve per se using market instruments. That will happen later. Here we are only looking at the dynamics of a yield curve given short rate. And I have a very nice two graphs. Let's start with the left-hand side. So you see here we have some scenarios. So we have a short rate under full-white, and then we stop simulation under point 10, and then given that point, we will be able to see the dynamics or how the yield curve, so like a forward yield curve, would look like under this model. So it's really nice examples of here we have Monte Carlo simulations until 10 years, and then from this point on, we will calculate yield curve implied by this model. And this dynamics, or let's say this kind of experiment, will be compared against, so this is full-white 1 factor, compared against 2-factor model. You will see the differences, advantages of extension, possible extensions to multi-factors. And also what we will also do, here will be also a video, very nice experiment performed that you can find online, where we will have multiple interesting graphs to see. So the first one will be we will simulate, or actually no, historically there will be evaluation of index of S&P. Then we'll be looking at the short rate implied by Fed fund. And then for every point in short rate, for example, we are here, then the graph, the simulation shows how the yield curve in reality was presented based on historical data. So that kind of simulation, we will see this kind of evolution in time. And this evolution in time of a yield curve, depending on, let's say, short rate or the spot rate of interest rates, this kind of phenomenon that we can actually observe from historical data, this will be we will be linking to the dynamics of full white and full white two-factor models. So it'll be a really nice exercise when we compare realities or historical data, the dynamics of a yield curve, and we will compare that against short rate models under the HJM framework. So this would be also very nice. I really like this, the link between the dynamics, the movement of the short rate or the spot rate of interest rates, the dynamics of a yield curve, which was seen at that moment, and then connection to stochastic models that we can actually try to replicate this kind of behavior. And then, of course, this yield curve that we will see over time, you will see it will have different shapes. And then these kind of shapes we can compare to our stochastic model. This lecture will be of two parts. So the first part we'll talk about affinity of a full white model, also exact simulation. Then we talk about the yield curves, what they are. So this is brief introduction without going into details how a yield curve can be implied for market data. And then we will go to extension of a single factor full white with multi-factor, and how this extension can be seen in this kind of comparison when we compare real market data against simulation that we perform. So here actually you can see here this blue line is the short rates. So this is basically in reality we see only one path of the historical one path, because we only have one events took place in the past. And of course in a simulation of full white we can simulate as many paths we want. So this, you see, it's a really nice comparison of one path, and this is here we have many paths, and if you choose one, we can see these dynamics of a curve. But the whole analysis will be discussed in this lecture. I think it's very exciting. Yeah. Before we build a yield curve, we need to understand how to price interest rate products. Then later, those interest rate products will be used as building blocks of a yield curve. Lecture 5 is this lecture where we talk about construction, pricing of different products available in the market. Again, we have 2 blocks, so we have 2-hour lectures, so each block is about 1 hour. We start with a simple compounded forward rate agreements, floating rate notes, interest rate swaps, and then we'll move to a little bit more, let's say, exotic type of contracts when we talk about options on zero coupon bonds, and then also measured changes with regards to full white dynamics. Here we'll be also talking about the caplets and floorlets and pricing of those under the full white model. When we talk about the pricing of, let's say, interest rate products that are linear, we always talk about products like interest rate swaps, when there is no volatility in the pricing necessary to perform pricing. If we have volatility which is needed, so for example options, then we need to have a model that will also simulate these uncertainties related to those options. Of course, the question will be why we need options, why we need those volatilities. And of course, ultimately, at the end of this course, we would like to simulate Monte Carlo paths for a model. And in order to simulate those paths, we need to calibrate that model to option markets. And of course, this is why we need information how to price options. In this way, we will be able to calibrate our model to those option prices. And then that would give us also, let's say, a realistic set of paths for short rate or any stochastic differential equation that later we can use in pricing of XVA or simulations of exposures and also value at risk. So here is a nice combination. This is illustration of a swap. So here we see we have a sequence, we have a, let's say, a sequence of cash flows where we exchange fixed rate against the float rate. And of course, the ultimate question is, what is a fair value when we have such a situation, when we have those kind of future cash flows? So all those, let's say, those future payments are uncertain, and how actually we can calculate them essentially in the linear world without actually using any volatilities, and how this can be linked to the measure changes and assumptions of models. So this will be also another very important building block, because this block, when we talk about interest rate swaps, forward rate agreements, and for example, here we have a floating rate note, fixed rate notes. Those will be building blocks, important building blocks for building of a yield curve. That will be discussed in lecture number 6. And indeed, lecture number 6 is about the building of a yield curve and multi-curves. So here it's a very important subject, not only in the context of XVA, but in general in finance, especially if we talk about pricing of any interest rate derivative. And actually in every asset classes, whenever derivative we want to price, we always need to have available yield curve. And that yield curve is calculated based on market instruments. So here we will spend 3 hours on that subject. We have 3 blocks. We will start with the dynamics of yield curve. So what are the possible shapes of a yield curve? How those shapes are related to market situation, whether the market is in a recession, which yield curve shape is good for banking industry, and which one indicates some kind of transitions between recession and recovery. And then we will go from the idea, I will explain the linkage between implied volatilities and also the concept of a calculation of spine point and building of a yield curve. In the block number 2, so this is a red piece with 4 elements, we will talk about the spine points. What are the spine points? And how we define optimization routine such that we can build a yield curve based on market instruments. Here I will also, as an exercise, I will show how to build a yield curve essentially on paper, so without any calibration. Of course, this will be a very trivial exercise, but at the same time it will be very illustrative how to build a yield curve if you have, let's say, very simple few cash flows, and how this yield curve will be constructed. Then we have a Python experiment. So here we will build actual yield curve. So we will calculate all those Jacobians. We will define some interpolation routine. And then based on market instruments we have defined in lecture number 5, here we will connect them together to get our curve. And then we will also confront it against the inputs, whether we are able to price back all the market instruments we have used to build this curve. And then in 6.7, I'll be talking about different interpolation routines that are applied in a yield curve. So in the yield curve, you can specify different interpolation routines, and I will explain the impact of interpolation routines and impact on hedging. So how this is important and why sometimes you may see risks, delta, especially if you talk about interest rates, and how this is linked to the choices of interpolation. And this will be also a very important part. In the third block, we will talk about extension of the single yield curve. So yield curve, which it's on a single curve, how to extend that with multi-curve, how this is related to the, let's say, prices that happened in 2008, 2009. And then also we will build multi-curve based on a single curve on the materials we have developed in former 2 blocks. And here again we have Python experiment, everything hands-on. Ultimately what we also do, so here's the yield curves from the department of the treasury, and then you will see there are some quotes. We will take those quotes from the market, let's say, and based on those quotes we will construct our curve, and of course given the interpolation. So this is also very important. Later especially we'll be using this construction of a yield curve when we'll be talking about the historical VAR calculations, shocks, and also obviously when we'll be talking about exposure simulations and XVA. Lecture number 7 is about the pricing of swaptions, and also here we'll be discussing concept of negative interest rates. So why negative interest rates are in the market and how to model them, how to handle, how to include this information and rates can be negative in your pricing engine. So in the first part, we'll be talking about the pricing of caplets and floorlets, pricing of interest rate swaps. So this will be a little bit of a refresher from previous lectures. And then we'll be talking about pricing of swaptions under the Black-Scholes model. So this is the first block. In the second block, it will be more advanced because here we will be pricing swaptions based on a full white or any short rate model. And this will be also important for our XVA engine, where we have to calibrate our full white model to the market, to the quotes of swaptions. And of course, in that way, we need to first be able to price swaptions using full white dynamics. Here, the famous Jamshidian's trick. So this will be, I will explain what is this trick about, and I will also show you some Python experiment to confirm that this methodology really works. This Jamshidian trick will be also used in the pricing of swaptions under a full white model or any short rate model, single factor short rate model. So it's 7.5. We'll be talking about the pricing of swaptions under the full white model, and then we move to the concept of negative interest rates, shifted log normal, shifted implied volatilities. What are those terms? How to think about it? How the concept of implied volatility has evolved? That we are not only talking about implied volatility as a parameter, but we also need to know the corresponding shift parameter. So this is something which is also, let's say, recent market development. And until we have, let's say, in the market negative interest rates, this concept will stay for a while. So therefore, it's also very important now to understand what is it, what is the impact of the shift parameter. Can you choose any shift parameter? What is the impact of that also on your implied volatility shapes? So all those topics we'll be covering in this lecture. Here I have prepared two graphs. Also, this is a simulation of a full white model. So in the past, for example, interest rate were at 5%. You see, I simulated Monte Carlo paths, and then some of those paths become negative. Not so long ago, people who once, or let's say also academia, considered this kind of phenomena that rates were becoming negative was considered to be a limitation and a it's a very big limitation of the model, and that many practitioners and also a lot of people from academia try to address by introducing improvements such that the rates cannot be negative. So this drawback of negative interest rates was always a challenge for people to address, because of course interest rates cannot become negative. At least this was the vision, the let's say common opinion. These days we see that rates are close to zero, and then of course the question is, can be what is the lower limit of rates to become? Is it 10%? Is it 20%? This is of course the evolution of over time of the concept of something of interest rates, how they evolve over time. And in this lecture, we'll be addressing both swaptions and also negative interest rates. What are those things and how to handle them? Lecture number 8 is about pricing of mortgages and prepayments. I have already mentioned before that this subject is very fascinating, as it combines or merges together the concepts of pricing under the risk-neutral measure and also pricing under the P measure. So from the risk-neutral perspective, we have a derivative that as a bank, in order to hedge mortgage portfolio, we have to hedge it in the market. And of course, pricing in the market is under the risk-neutral measure. However, if we talk about a client, and of course clients may prepay their mortgages, this means that their decision is not based necessarily on, let's say, optimal or rational behavior. They may behave irrationally, and that kind of gives us this kind of relation to the P measure. In this lecture, which is, as you can see, longer than what we have seen before, here we'll be discussing the impact of clients and their decisions of prepaying their mortgages. Prepayment is defined as the extra sum that you would pay back your mortgage, and this is on the top of your contractual obligations, and how this impact of those prepayments would affect, let's say, position and hedging from perspective of a bank. So this lecture is divided into 4 blocks. We will mainly discuss the bullet mortgage, so very simplistic, very simple mortgage type. And then the more important one is the annuity mortgage. We start with bullet mortgage in order to start with something very trivial and very easy to understand. And then we will move to something much more advanced. And for every part here, we will also have Python experiment. I will explain you the cash flows associated with each particular mortgage type, and also how those prepayments are affecting the, let's say, the payment schedule from your client. And of course, this will be related, of course, to these two types of mortgages. Then we'll talk about the prepayments determinants. So why people decide sometimes to prepay their mortgage, and how this is related to so-called prepayment or constant prepayment rate, CPR. Once we have people who are prepaying their mortgages, that would also influence the contract or the mortgage portfolio, and that would be linked here to index amortizing swap, where we have to, in order to price this derivative, we need to include the refinancing incentive. Then, of course, the interesting part is that we will link the refinancing incentive of a customer to market observables. So we will basically say that a client who would like to prepay, he will not do it only based on his, let's say, P-measure incentives, whether, for example, he has won a lottery or not, but here we will link it to the market observables, saying that clients will prepay because, for example, interest rate in the market has decreased. And that would make it more attractive for the client to prepay. So here we will link it, the prepayments, to market observables, and then we will describing this kind of connection to pricing of index amortizing swaps. And I will explain also how this pricing of portfolio of mortgages would be influenced by different refinancing of financing incentive of a client. So we will change different incentives, and we observe the impact on that on our, let's say, amortizing, or let's say on the payment schedule. And then something, and also another risk factor related to mortgages is the so-called pipeline risk. And this is also a kind of optionality that clients often have when they when the price of the quotation when they want to have a mortgage differs from the settlement of the mortgage. So this means that if a client would like to announce to a bank that he would like to have a mortgage, then he will get a quotation rate. However, if the rate at the settlement, so the moment the contract is signed, if the rate has moved in, say, in favor of a client of course would like to have a favorable rate, then client may choose, of course, naturally he will always choose the lower rate. And of course that type of risk also needs to be handled from financial institution. And this type of risk also we will discuss here. And then we will finish with a lecture with a summary on homework. So this is rather extensive. And however, it's a very fascinating subject, especially if we talk about incentives to prepay. And this is nice link between, like I said, between real world and risk neutral measures. In lecture number 9, we will talk about the modeling of multiple asset classes at the same time. This is actually related to modeling of the so-called hybrid models. So we are not simulating a single stochastic differential equations for stock or interest rates or or FX, but we'll be simulating multiple stochastic differential equations, and those processes will be used later to simulate possible scenarios of the future evaluation of future risks that can be affecting our portfolio. So of course, correlations, especially if we talk about diversifications, correlations between different stochastic differential equations will be important. In the past, before the crisis from 2008, 2009, those type of, let's say, hybrid models were used for pricing of exotic derivatives. Therefore, derivatives that have involved multiple asset classes. After let's say that crisis, the interest in those exotic derivatives has decreased. However, because of the concept of XVA, exposure calculations, and also VAR, Monte Carlo VAR, those exotic contracts or hybrid models, they are still important because now we can see this exotics is not as a trade for a client. However, from the risk management perspective, we also need to apply the same technology to price those, to show the risks or calculate value adjustments like XVA. So you see, it's not, those models are not anymore used as the contracts to be bought or sold. However, they are coming back and they are very popular and actually important these days from the regulatory perspective to use those hybrid models to price valuation adjustments and value at risk. So lecture number 9 discusses those kind of hybrid models. We'll be also talking about extensions with stochastic volatility. So very interesting lecture, especially for a quant. Here we have 2 blocks. In the first part, I'll be talking about hybrid models and how they can be used for XVA and VAR. And then very simple Black-Scholes whole white model, so hybrid, where we have a stock dynamics and also we have stochastic interest rates. And then we will finish this block with a concept of implied volatility in the case where we have stochastic interest rates. So how stochastic interest rates, how to think about the concept of implied volatility if we have stochastic interest rates. In the second block, second part, we'll be talking about stochastic volatility models, stochastic vol models like Heston, for example, and how you can expand, include stochastic interest rates that are actually correlated with the stock process itself. And here to show you also the impact of correlations between correlations between interest rates and stock itself, we'll be talking about diversification products. So we will define kind of hybrid payoff, and we'll be looking at the impact of the value influenced by the correlation coefficient. More details in 9.6 about the Heston whole white hybrids. And then in the later part, we'll be talking about generic Monte Carlo framework for pricing and simulating hybrid models, multidimensional hybrid models involving multiple asset classes. In particular, as an example, I will show you how to simulate with Monte Carlo almost exact simulation of the Heston whole white model. And we will finish with a summary and number of homework assignments. It is not enough to be able to simulate stochastic differential equations assuming different asset classes. Ultimately, we need to be able to price those contracts that are defined under different asset classes. So it's not only about simulating foreign exchange. We really need to understand also what are the foreign exchange products that will depend on those simulated paths. And only then we can combine them together in order to calculate exposures and then later, of course, calculate some risk measures. So in lecture number 10, we will be discussing 2 asset classes that are very important, and of course, often portfolios include those derivatives. Here we'll be talking about FX, so foreign exchange, and also inflation. This lecture will have it's about 3 hours. We have also 3 blocks. We will start with a concept of foreign exchange, where it comes from, how it is related to different asset classes, and also a little bit of history of development of the floating currencies that we currently have. This was not always the case that all the currencies were afloat or full fiat. There is some nice historical development around that. And then we start with a definition of contracts like a forward FX contract and then cross-currency swap, which will be naturally we could add later to our portfolio for which we would like to calculate risks. In the second block, we will talk about options on FX. So again, we cannot forget about volatility products like options, because later those options would be used for calibrating of our stochastic differential equations for the FX market. So of course, it is also important to understand what are the products in the market and then how to calibrate potentially. And then also extensions to Heston FX, so stochastic volatility FX market. Here is a very interesting concept, because if we talk about extensions or hybrid models involving FX, then there is something, it's not only about defining stochastic differential equations. You will see that the concept of measure changes that we have discussed already in lecture number 2, those play a very important role here, because the dynamics of the processes after the measure changes will be slightly different, unexpectedly different. So there will be some kind of quantum correction element that will be present in a stochastic volatility, essentially, of the model, and that will be very problematic to handle. You will see that quantum correction measure changes. It is trivial, or let's say it is not so difficult if you deal with a single factor models. However, if you have multi-factor models, changes of measure, it is not very difficult, but if you don't do it properly, may lead you to significant error. So you can really destroy your model if you change your measure incorrectly. And then here also, as the end of this second block, we'll be talking about pricing of FX options with stochastic interest rates. So this will be also kind of hybrid spirit, where we have not only, because it's a FX, this means we not only have interest rates in a domestic, let's say our currency, our economy, but this also involves interest rates from other economy. So of course our hybrid is growing essentially in size. And in lecture number, this is lecture number 10, but in block number 3, we'll be concentrating on concept of inflation. I will show you how the definition of inflation evolved over time from something which was purely monetary. Now it is completely defined on baskets of goods. So it's also very interesting how the definition of inflation evolved over time, and then later, what are the market instruments that essentially the underlying of those market instruments is inflation. So this is also important. And then, of course, modeling of inflation and with SDEs. Why inflation is with FX? Because those two categories, so those two asset classes, from the modeling perspective are very similar. And this will be also explained in this lecture. And again, we will have a few homework assignments. Market models like LIBOR market model or LIBOR market model with stochastic volatility will be discussed in lecture number 11. Here is not only about market models, we'll be also talking about the convexity adjustments. What are those and how to use them in practice, how to calculate those so-called convexities. So we have two blocks here, each of them will be about 1 hour and 15 minutes. We start with a history of the, let's say, development of interest rates, and also what is the motivation for market models like LIBOR market models. And this will be, of course, related to the HJM framework, so Hit-Jarrow-Morton framework. We will specify the model dynamics, so here and also here. We'll be talking about, we start with modeling with a measure P. So we always start in the interest rate world with dynamics under the real world measure, and then using HJM technique, we'll be always transferring this model defining to the proper measure that we would like to use for pricing of derivatives. So always P measure means calibrating your model to some historical data, but of course in finance we are calibrating to data available right now, but not historical data. This means it's a risk neutral, it's implied from the market, it's not historical. Then we go into specification to so-called log-normal LIBOR market model, and what are the measure changes, what are the typical measures used for pricing. Here in particular, I'll be talking about terminal measure and also spot measures. I will discuss the differences between the two. Of course, we will derive those two measures. What are the advantages, disadvantages, and also we will cover here the topic, what is the market practice? Why one measure is more preferred than other one? Then we will move to stochastic volatility LIBOR market model. So we will extend log-normal case with stochastic volatility. We'll be also talking about the smile and skews under LIBOR market model. So you will see this is actually interesting problem here because the dimensionality of the model and also the continuous necessity of measure changes under the LIBOR market model, then some standard stochastic volatility models like Heston is not suited. And in this part, I will explain you what's the problem with the Hester model. It will just simply apply this model to the LIBOR market model. And of course, in this part, we will address those limitations with a different stochastic volatility model. Then I will discuss also the freezing technique, and this freezing technique is related to these two graphs. We started with a tank, we started with a model which solves the problems, although of course it's very difficult, let's say it's very expensive to maintain. However, if you apply techniques or you abuse techniques like freezing techniques, even the tank becomes useless. So it's not a problem solver, but maybe actually damaging the whole pricing framework. So here we'll be also discussing what is actually the freezing technique, why it is used, and what are the risks associated with abusing of this technique. And the last part, we will concentrate on convexity correction, what it is, how to recognize that we have to deal with a convexity correction. And then the last part here, I'll be talking about how to, in a convexity correction, how to include the whole interest rate or the smile and skew present in the market in order to address the problem of convexity correction. So this will be it's maybe longer, but it's a really nice piece of materials, because here we talk about a LIBOR market model. Very much detail will dive into the measure changes, especially in this high dimensionality model, which is a LIBOR market model. And then we also talk about the convexity adjustments. So those are really fun topics for financial engineer. If you like to be financial engineer, you should not be afraid of those two subjects. Ultimately, in this course, we would like to perform XVA simulations. So we would like to calculate CVA, BCVA, and FVA. And this is what we'll be doing in lecture number 12. So this lecture consists of 3 blocks, where we will start with discussion, what is CVA, or the credit value adjustment, what is the motivation for this adjustment, why it is needed, and how this is related to hybrid models. Then we will talk about exposures and potential future exposures. What are those and how those can be used in calculations of those value adjustments. And then, of course, here the expected exposure. So this is, let's say, the first block of this lecture. It is more introduction of the concept of exposures, expected exposures, potential future exposures, and how this is related to our, let's say, portfolio and risks. In block number 2, I will show you so-called sanity checks. So I will show you a few examples for which expected exposures can be calculated analytically. So we have a few examples. This will be related to swaps, foreign exchange, and also some other contracts for which we can have expected exposures calculated analytically. Of course, you can ask, what's the point of calculating this analytically? And of course, is it really necessary to simulate your model if you can do it analytically? So of course, those are really special cases. So if your portfolio would consist only of one swap or one stock or one FX forward or FX swap, then indeed you can, in this idealized world, calculate those expected exposures. In practice, in reality, portfolios would involve multiple contracts. Sometimes it goes into hundreds or even thousands of different contracts. And of course, here, the sanity check, what I meant here is that if you have implemented your XVA engine, your exposure calculator, it is important to double check whether your simulation corresponds to analytical expression. And this is also this 12.4, it is actually the purpose, is that purpose. Then we will go into Python simulation, so we will simulate exposures with Python. This will be for 1D case. And then we will talk about the exposure generation for portfolio of assets. How to do that. So of course, using those hybrid models we have defined in the previous lectures, how to use those for portfolio evaluation. And then we go a little bit in the theory side. We will derive CVA adjustment. So we will start with a simple contract between two counterparties, and using, let's say, assumptions or imposing the additional feature of the contract that the counterparty we are dealing with could default. From that, this will be our starting point. After some derivations, we will arrive of the credit value adjustment correction, or adjustment that needs to be included into price of derivative. And then we will talk also about practicalities. What are the market standards regarding the approximations? As the extension for CVA, we move to BCVA, so the bilateral credit value adjustment. This means if both counterparties take each other's risks of default in order to price derivative. And this is important because if you just look at the CVA, if you have two counterparties that could default, the problem with CVA will be that there will be no, let's say, price discovery, because if one counterparty thinks that other can default, and the first one thinks that if there is, let's say, counterparty A and B, and we include this counterparty in default probabilities, then there will be no price alignment between the two, so there will be no transaction between these two counterparties. So, and all the details, of course, you will find in this lecture. We'll go through all the steps in order to derive also BCVA, how this is related to CVA, and how this price discovery process can be completed. Then I will also show you how what we have learned about the CVA, BCVA, how this simply can be extended to the funding value adjustment. And then we talk about also some kind of practical aspect of trade attributions. So how to decompose a portfolio consisting of many trades into individual CVAs per trade. So this will be also very much practical. And again, we end up with some kind of small project where you will have to build your XVA engine or extend the engine I will provide in this part with some additional features. So this will be also very much hands-on assignment. The final lecture of this series is lecture number 13, where we'll be talking about the value at risk and expected shortfall. In the context of value at risk, we'll cover aspects like historical VAR, stressed VAR, and also Monte Carlo VAR. So it's VAR based on Monte Carlo simulation. This will be, again, hands-on exercise. We will start with some theoretical aspects about what are the risk measures, and also later we will move into Python coding. We will discuss, or we will code two subjects, of course, historical VAR. So again, we will download data from the market, historical yield curves. Based on those curves, we'll construct so-called scenarios, and we will use those scenarios to estimate value at risk for portfolio that we will define. So you see, it's a rather practical and very, maybe in some context you can say it's a complex but very practical. Typically, when you look at the literature and also in the standard books, people explain you these algorithms about the VAR, but they really don't tell you how to build a curve and actually how to look at the full experiment. So in this lecture, we will really concentrate on computational aspects, on simulation aspects. And at the end of this lecture, you'll be able to evaluate your own value at risk, expected shortfall, given, of course, the knowledge you have gained in the whole sequence of these lectures. So first part of this lecture is about value at risk, so theoretical discussion, stress VAR, motivation, differences between the two. We will confront expected shortfall against the coherent risk measure. So we have some kind of a classification of different risk measures, and then value at risk and expected shortfall will be confronted against those kind of requirements for being coherent or good risk measure. In the second part, this will be more hands-on. We will be doing the HVAR or historical VAR experiment based on real market data. So we will build a portfolio of interest rate swaps, and we will also gain, let's say, use our knowledge regarding building of yield curves. So based on historical data from interest rates, we will rebuild our curves, build scenarios, and then estimate VAR and expected shortfall based on the simulation results. And we, of course, I will discuss all the difficulties and problems associated with the simulation, where are the parts that you should concentrate, and we will go step by step how to build up your VAR or value at risk engine. Another point I would like to discuss here is the problem of missing data, arbitrage, and problem of regredding. So those are, let's say, practical additional aspects if you work in a bank or other financial institution that often you need to take care of. Then VAR computation with Monte Carlo. So here we had very practical hands-on exercise. Here we will continue. We will be looking at a different aspect of VAR, but not VAR based on historical data, but on the Monte Carlo simulated paths. And those paths will be, of course, simulated for the future, not based on historical data. So, of course, I will show you how to compute this VAR, given, of course, our idea and expertise that we have gained regarding Monte Carlo simulation, short rate models, and exposure calculation. We will finish this lecture with a backtesting idea. So how to test your VAR engine. What are the consequences if your model doesn't satisfy that requirement? And actually, what is the whole idea behind the backtesting? And here again, although this is the last lecture, still we have to do homework. You'll be asked to also hands-on exercise. You have to extend the functionalities of the provided Python code. So this is it. So the lecture number 14 is about, let's say, summary of this lecture. So we are on the top of this mountain. So we had, after those 14 lectures, unfortunately it will be longer than 14 weeks because the lectures will not be released in those big chunks because nobody will follow those 4 hours, let's say, of lectures per week. But slowly we will climb up the mountain. I have actually checked, so the record to climb the mountain from the Mount Everest from the base camp is around 8 to 10 hours. Of course, these are disputes. There are still disputes who was the fastest, but here it will be much more. We have about 32 hours course. However, we will do it in a great style. So we are not running, chasing the mountain. We will achieve our goal to get to the final, to the summit of this mountain, but we will do it in a very nice style. We will build properly all those camps, and every camp, every lecture, we gain additional knowledge such that will support us further to go to our ultimate objective, which is the valuation adjustments XVA and also calculation of value at risk. So this is the plan. This is the plan of the whole lecture. Of course, this is the plan. Of course, those lectures are already recorded, so I already know that those are are good materials and everything is well planned, such that actually we can reach to the summit. So this will be a very enjoyable tour. Enjoy this course.